In case you're wondering how you could improve the security of your HTTP-based API without being too intrusive and without making it too hard to use for the developers who are actually consuming your API, you definitely want to take a look at HTTP message signatures, which is a current draft of the IETF, the Internet Engineering Task Force. So you can take a look over here. As of this recording, it's draft number 6. And yeah, I think it's a very interesting and smart solution on how to provide message integrity and message authenticity when you are using HTTP. But let's make an example to understand what exactly they are proposing. So imagine you have two systems and they are talking to each other. So you have system 1 and maybe there's like a microservice running here, and this service is trying to send a request to the other system. And usually the way we do that is, right, we use HTTPS. So that means we use HTTP over TLS, so TLS, transport layer security, to make sure that our communication is like encrypted and there's like no man in the middle attacks or anything like that. So this is like TLS, and this is all fine. Now the thing is that usually this service does not directly talk to the service that is actually receiving and processing the request, right? Usually you talk to some form of API gateway, which is handling like all the certificate setup and which is also doing a little bit of routing within the system. If you make a request to the API gateway, then you basically have a secure communication channel between the service and the gateway, but you don't know what is happening afterwards. So what is happening a lot like with these gateways is that they actually terminate the TLS connection. So that's why it's called TLS, terminating gateway. So once they receive like the data you have sent, they just forward it with HTTP. Because they say, well, I'm already in my own system, so I would assume this is like a secure environment. And that's why I'm directly forwarding the request with HTTP. No need to do additional certificate handling. Now, some gateways, or like in some systems, the gateway is set up in a more secure way. So that means the communication between the gateway and the service itself would also be via TLS. So that's of course good, because then nothing in between can happen. But still, in the end, don't know, or like this service in the end doesn't know whether the request that it's actually receiving is really exactly what this initial service has sent. Because bear in mind, this gateway is supposed to do a couple of things. So it's supposed to do routing, and it might also modify the HTTP request. So for example, it might add additional headers, or it might like reorder headers. In HTTP, it is totally valid to swap the order of headers as long as you have different header field names. If these two names for these two headers are different, you can swap them. If they are the same though, this operation would be illegal. With this whole setup, the question is, how can this service know that, for one, the message it receives really comes from the actual sender, and how can it be sure that this message has not been modified somewhere in between in an unauthorized manner? And these are the two properties that we're trying to achieve with HTTP message signatures. So we want to achieve end-to-end authenticity, so the data originated from its purported source, and message integrity. And now you might say, well, hold on a second. I mean, for this, it's quite clear, right, that for this connection here between this and this service and this gateway, it's kind of clear that we need some form of authorization. So we need, I don't know, HTTP basic auth, OAuth, client credentials flow, like anything to make sure that the API gateway knows that this is a legitimate request. And that is totally true. You definitely need that. But still, this service does not have the guarantee that the data it's receiving is actually coming from system 1, because the API gateway might modify something, right? If it's misbehaving, it might even modify the body, and there might even be more hops in between, depending on how your network is set up. So even if you have a proper authorization between like the system and the API gateway, you don't know, or this service doesn't know whether it's really coming from the correct source. And the question is, well, how do we deal with the fact that TLS connections might be terminated by API gateways, that API gateways might add additional headers, and that we might perform specific message transformations that are allowed by HTTP. So for example, reordering header, adding specific headers, removing them, adding whitespace, removing whitespace. All of these are possible, but these transformations are actually fine. So as long as the semantics and the content of the message is not changed, those transformations are fine. But in the end, we just don't know whether the content has been changed or not. And the first intuition might be, well, in order to kind of achieve authenticity and also integrity, why don't we just use something like a JSON Web Signature token, right? So we just take the body, we take whatever we send and wrap it into our claim set, and then we sign this. Please make sure to use digital signatures and not message authentication codes, because with message authentication codes, you have a shared secret. That's not so good. So in theory, that solution kind of works, but not really, because you're only protecting the body, but you're not protecting like the headers. So that means anyone could just, or like any gateway could just modify the headers and no one would ever notice. By the way, if you're not sure what JSON Web Signature tokens are, please make sure to check out the playlist on my channel where I explain JSON Web tokens, JSON Web Signature tokens, and JSON Web Encryption tokens in detail. And one more approach I wanted to point out, but that approach doesn't really work, is, and there's another method that kind of doesn't really work, but I just wanted to mention it here explicitly and explain why. So you might think, okay, why don't we just add this digest header and we just hash like the body, and then if something changes in the body, then we will know. Well, the thing is that this header here is not based on asymmetric cryptography. So that means anyone can just change like the body and then recompute the hash and basically swap out this particular header, and nobody would ever notice. And in addition, you have the situation that you're only protecting like the body, but you're not protecting the headers. And this is exactly where HTTP message signatures come in. So HTTP message signatures was exactly designed for this purpose, to make sure how can we have end-to-end authenticity and integrity while using HTTP. And I've taken like a few sentences out of the spec to kind of briefly explain what the goal is. So goal here, end-to-end integrity and authenticity for components of an HTTP message. And then it goes on to say, yeah, this mechanism allows applications to create digital signatures. Well, that sounds good. Or message authentication codes. Nah, I mean, okay, but please use digital signatures wherever possible, over only the components of the message that are meaningful and appropriate for the application. Well, that is interesting, right? So you can basically say, okay, particular parts of the message are important and I'm only going to sign those and I don't care about the rest. And if there's some proxy and this proxy adds some additional header to it, then I don't care about it. And in addition to that, it says, well, we need strict canonicalization rules to ensure that the verifier can verify the signature even if the message has been transformed in any of the many ways permitted by HTTP. Also makes sense, right? Think of swapping the order of the header fields, or think of adding and removing whitespace. Bear in mind that HTTP fields like headers and trailers, like the case is not important. It's case insensitive. So this might also lead to issues, right? Because if only one character is different, the signature validation would fail. Yeah, and then there's an additional thing I also wanted to mention. You can also request the other party to say, hey, please provide me like a signature when you reply to my request. And this is kind of interesting because it's sort of like, please give me a receipt that you actually received what I was sending you. And one important thing that I want to point out with this draft is you can actually have multiple HTTP message signatures in the same message by different signers with different algorithms. Approach is like very flexible. So before we can understand what the draft is actually proposing, we need to understand the vocabulary. And they are talking about HTTP message components. And it goes on to say that, well, an HTTP message component is a portion of an HTTP message that is capable of being covered by an HTTP message signature. Okay, fair enough. So you can take a specific part of a message and then you can say, I want to sign this, and the ones that you don't mention are not signed. Okay, that's kind of cool. So in practice, this means if you have an HTTP request, which has the headers, the body, and trailers, you can say, well, I only want specific headers or specific fields to be signed, and then these fields are going to be taken care of. So basically any HTTP field, so that means anything that is in the header and anything that is in the trailer, is an HTTP message component. And by the way, if you're wondering what trailers are, so trailers are fields that can be added after the body. That's why they're called trailers. And this is a feature that is not really that common. So it has been there since HTTP 1, and some protocols are actually using it, but usually most fields are like in the headers. And that's why the specification also constantly talks about HTTP fields and not headers, because theoretically you could also have trailers, so trailing headers, and these come after the body. But essentially they say, okay, any HTTP field can be a message component, and they say, okay, the HTTP field name is the message component identifier. There's some canonicalization rules that are being applied, so everything must be lowercase, for example, and that is like the message component identifier. And the message component value is the actual value of the HTTP field. And by the way, if you have multiple HTTP fields with the same field name, then those are being joined with a comma and a space. Bear in mind, as I said before, you cannot reorder headers if they have the same field name. If they had like different field names, then it would be valid to reorder them. So like any intermediate hop can reorder them. But if they have the same HTTP field name, you cannot reorder them. And that's why this approach works. So you don't have to worry that, okay, what happens if this second header comes first and then this one comes and then everything is going to be totally messed up. No, simply because that's not allowed by HTTP. So this is one thing. So HTTP fields are message components. And another thing that is also a message component are the so-called speciality components. So these are things that are not directly found in headers or trailers, so not found in HTTP fields, but then can still be included in the signature. And those make a lot of sense. So for example, the HTTP verb, so get, put, post, delete, and so on, this is not part of an HTTP field. So it's not here or here, but it's sort of like outside, but you still might want to sign it. Same thing for the port, the same thing for the scheme. And there's actually more than these. So if you go to this draft, then you can see all the initial speciality components that they have registered. So there's like more, there's like query params, query, the path, the full URL, so the status code, and also request response. So there's like quite a lot of those, but I haven't included them in the list just for simplicity. But the most important one, and this is the one that I've actually also marked in bold, is this signature-params speciality component. And this is actually, I would say, the most important one, because it contains metadata on how to generate the signature and how to verify the signature. So which message components are part of the signature, and also when was the signature created, what type of signature is it, like which algorithm was used and which key was used. The idea now is, if you have an arbitrary HTTP message, you just say, okay, I'm going to pick the message component identifiers that I want to sign. So for example, I say I want to sign the host, and I want to sign this cache control field. And then I'll provide a little bit of metadata. So I say, okay, this message or like this signature was created at that point of time. So this is like a Unix timestamp. It expires at that point of time. So by the way, this is like optional. This one here is recommended. And this is the key ID that I've been using. So this is obviously important, right? Because if I throw your random signature over the fence, then you say, well, how am I supposed to verify this? I don't know what it is, and I don't know which key has been used. That's why you use like key ID. There's also additional parameters you can use. So if you scroll up here in the spec, you can see you can also specify the algorithm. Although it's better to derive like the algorithm from the key ID. Yeah, and this is like how the signature params looks like. So you basically say, I create an ordered set of message component identifiers. I add a couple of metadata, and this is how my signature is going to look. And then you generate the signature. So generating the signature is actually pretty straightforward. So what you do is you come up with this ordered set of component identifiers in a canonicalized form, right? So everything lowercase, no whitespace in between. So for example, you might say, okay, I want to sign the cache control header, and then I want to sign the method. And then you add a little bit of metadata. So you say, okay, this signature was created at that point of time. So this is a Unix timestamp. and it expires at that point of time, and the key I've been using to generate the signature is, or the key identifier, not the key itself obviously, but the key identifier is like this one, and the algorithm is like this one. And by the way, in terms of security, it's obviously better to derive the algorithm from the key identifier, right? So somewhere in your database you should say, for the key with this particular ID, I have been using a particular algorithm. Yeah, so even though you can add this from a security perspective, it would be better to not do it. And there's also more to it. I think if you go to section 6.2, you can see they also support this nonce parameter over here. Okay, so basically you come up with this list and say, first I want to assign cache control, then assign the method. And then you actually, based on all of this, you can actually generate the input string for the signature. So you say, okay, I go through this list, and then I look at my HTTP message and say, okay, cache control, what is the value for cache control? Well, it's like max age 60, must revalidate. Bear in mind that in this example here, we had these two headers, but we joined them together and made everything lowercase because of the canonicalization rules. I just wanted to mention that here explicitly as well. Then you make a new line, so not a comma, but a new line. And then you continue with the next item. So method is like get. So you add this method here, make a colon, and then you add get. And at the very end, when you're at the end of your list, then the last item is always the signature-params message component. And the reason for that is that with this, you force that you always include the metadata for the signature in the signature itself. So this is just important from a security perspective. Yeah, and this is like the input string. And this is then actually what you pass to your signing algorithm. Now, this thing, or like the spec supports, pretty much like the standard algorithms for signing things. So as you can see here in the spec, it supports RSA, specific versions of RSA. It even supports HMAC. I would not use that honestly, because you have a shared key that's not so good. And ECDSA, which is like pretty decent, and also the whole JSON Web Signature algorithms, excluding none as an algorithm. Just wanted to mention that explicitly because that has created a lot of issues for JSON Web Tokens. Yeah, so this is basically the input, and then you use a specific algorithm to sign it, and usually you derive the type of algorithm, or the receiver derives the type of algorithm that you've been using from this key ID here. Okay, and once you run this through your signature algorithm, you get some value out. And now we have two more steps. So we need to obviously tell the verifier how to generate or how to regenerate this input string, because otherwise the message cannot be verified. And the way you do that is you add an additional header to your request, which is called signature input, which is a dictionary. And this dictionary you assign like a unique key for the signature, right? So this just has to be unique within the HTTP message. So you say, okay, this signature that I've been generating, I'm going to call this signature 1. And here is like how you can regenerate the input string, and then you add like this list with all the metadata. And yeah, that's it pretty much. So you add this to the message. This is one header you add, and you would obviously leave all the headers exactly as they are. And then in the fourth step, you would, of course, also add the actual signature, because this is what we care about. And this is also a dictionary. Yeah, so you would say, okay, the signature for sig1 is actually this. And by the way, the colon here is a way to indicate that we're now sending bytes, or like base 64. And if you're wondering about the syntax here, about like why is there like a bracket and then a semicolon, is that somewhere like specified? Yes, there's like a new RFC for how field values should be structured. So they essentially define a couple of data types, and that includes dictionaries and lists and inner lists. So I've already made a video about it, so you can go through the like this RFC, and then here it also explains like what the syntax is. So if you're surprised about the syntax, this is just using like the latest RFC. Yeah, and then you add these these two headers, and that's it pretty much. Now, one question you might have is, why do I need to assign like a unique ID for this signature here? Why can't I just attach it and that's it? So why does it need to be a dictionary? And the reason is that, as we said before, you can actually have multiple signatures created by multiple signers with different algorithms. For example, you could say, or we could imagine that the signature 1, in our example above, the signature 1 could have been created by system 1. And then the proxy here, or like the API gateway, could add an additional signature on top. So you can have as many signatures as you want in principle. And that is why it's like a dictionary. The only condition, obviously, is that the key has to be unique. So in that case, you would have two signature-params speciality components where you can sign different things. Then you have two different signatures in your output. And these are then, as usual, added to the header. And then both can be verified if needed. And the interesting part of all of this is that you can actually sign signatures, like the output of signatures themselves. So for example, the proxy here could say, okay, look, I'm only adding like a forwarded header. So what I do is I take the value of signature 1. So I'm going to take a look at the signature field, and from there I'm going to add the value of signature 1, that's like this key identifier, and then on top of that I also want to sign the forwarded header. So you don't have to repeat the whole list from before, but you can just add signature itself as input for another signature, which is kind of an interesting approach, but it also makes things a little bit complicated. But just wanted to point out that in theory you can have as many signatures as you want from different signers with different algorithms. And there was one question left, and this is actually what I was wondering. Well, what about the body now? So, I mean, now we've been talking about signing HTTP fields and these speciality components, so in general, HTTP message components, but how can I actually sign like the body? So the thing is, in the spec, it says that you can only sign HTTP message components, and as we said before, an HTTP message component is either an HTTP field or like the speciality component. But what about the body? I also want to integrity protect the body. And the thing is, you cannot directly do that. You can only do it indirectly, but that is good enough. So what you can do is you can just say, okay, for the body, I'm going to compute the digest header. So I'm going to compute, for example, the SHA-256 value. Then I have like a digest header, which is the hash of the body. And then I actually sign the digest header. And with this approach, you can actually not only protect the headers, but also the payload. So the way this would work is you have like these dates here, you have like this digest value, and then in your signature params, you just mention, oh, by the way, I want to use this digest value. And then these two headers would be added to your request. And that's it. And this is actually what I like about this RFC. So I think initially it's not so easy to understand. Like if you read through this RFC, it might take a little bit of time to understand it, but overall it's a pretty smart solution. And I explained the whole background of this thing now. So the only interesting thing to understand, or the most important thing to understand, is you have two additional headers. One header which contains a dictionary, and in this dictionary you say which message components are signed, and then you have another header which is also a dictionary which contains the actual signatures, and these can then be like verified. And with this you have a very, very flexible structure, and the nice thing is it's quite unintrusive, right? If we were talking about JSON Web Signature tokens, you would have this structure here in the body. You would not have that with HTTP message signatures. You would only have additional things in the header. And then, if you're just testing or if you're connecting to this API, you don't have to mess with these signatures. You could also think about, just deactivating it in some test environment to make it easier to use for the developers who are using your API, and then only activating it in production. So overall, I think a very interesting approach, very nice. Very useful if you want to design nice and secure APIs. And yeah, looking forward to see what is still going to be done with this draft. So very good work in my opinion. Cool, so that's it pretty much for this video. Today it was a little bit longer, but the RFC was also a little bit more complex. So I would say thank you so much for watching. Leave a like and subscribe to the channel. Let me know if you have any other RFCs that you want me to review. And yeah, if there's anything, just let me know, and I'll see you in the next video. Bye bye.